In the previous videos, we solved several ODEs with different kind of boundary conditions. We discussed Dirichlet and Neumann boundary condition, both homogeneous type and non-homogeneous type. We introduced boundary functions and superior boundary functions so that non-homogeneous boundary condition could be satisfied. Also, we saw there are limitations on the choice of basis functions. That is, they should be 0 at specific points of the boundary if Dirichlet boundary condition has been specified, and the derivative should be 0 if Neumann boundary condition has been satisfied at specific parts of the boundary. Also, we saw that the construction of these boundary functions, especially to satisfy the Neumann boundary condition, is a bit tedious and challenging. And we also saw that the differentiability requirement of the basis function is also a constraint on choosing the basis function. Okay, so we to solve these issues, we in the previous video we introduced what is called a weak form. We just introduced it and we said that it is this transformation of your weighted residual statement into a more usable form, so that these problems of satisfying Neumann boundary condition and differentiability of your basis functions is somehow solved or partially solved. So let's see how can we get to that this weak form in this video. So we'll start with what is called integration by part. Okay, so this is the mathematical transformation, or this is the only step that you require from the weighted residual statement to get to the weak form. Okay, so why do we want to do this? Why do we want to do integration by part? Let's see. This integration by part can be used to transform a second order derivative to a first order one. Okay, by doing this, the second order differentiability requirement is now reduced to the first order one. Okay, for example, consider this weighted residual statement of some problem. Okay, now note that these are inner products, okay, not simple brackets, and now the requirement on the basis function comes from this, okay, the differentiability requirement. Now what if we can convert this by integration by part into a UH dash? Okay, let's see how can we do that. So this is the problem that we saw, and we want to convert this now using integration by part that we all familiar with in introductory integration course. So you convert this into these two terms. Okay, this part, this is a inner product of U double dash with V. Now we have converted it. Note that this is not the trial solution yet. This is just the exact statement. Okay, this is an infinite space now, not the finite dimensional space. Should be V, so let's say we call it V infinity. Now we have moved one derivative, this, from here to here. Correct? See, U dash, V dash. So and also in the process some boundary term. This boundary term has appeared. Okay, note that this boundary term contains U dash. And what is Neumann boundary condition? It is satisfying this U dash itself. Okay, so we can directly use this term. We can just put in the value of U dash, whatever we want, whatever the problem requires, into this expression to directly satisfy the Neumann boundary condition. We need not construct those g of x, those superior boundary functions, to satisfy this condition. Okay, so you can see that the implementation of Neumann boundary conditions is now very natural. We can simply put in the values. Okay, these terms came out naturally as a result of integration by part of the weighted residual statement of specific term in the weighted residual statement. Okay, so that's why these type of boundary conditions are also called natural boundary condition. No, we call them Neumann boundary condition, and they're also called natural boundary conditions because of this fact, because they come out naturally. Okay, so earlier we constructed our basis function to satisfy this Neumann boundary condition. Now we need not do that. We simply construct our basis functions to satisfy the Dirichlet boundary condition. Okay, and we input the value of our Neumann boundary condition in this term. Okay, but we'll be losing something. We'll see in the example what are we losing. Okay, there's something happening by doing this step, and then using the approximate solution we'll lose something. Okay, now just to summarize the stuff, we had to satisfy the Dirichlet boundary condition earlier, the Dirichlet or Neumann, and we had to design our trial functions. Okay, that's what we have discussed earlier. We constructed our trial solution something like this, and now we need not do that. So now we have weak form, we can simply put the values. We need not do anything special, so they are coming out naturally. That's why they are called natural boundary condition. Okay, moving to the next slide. Okay, so this is the weak form now, and this term, this boundary term that is evaluated over the boundary, note that this term is now evaluated 2 points because boundary is the 2 point. For example, if you are in 2D space, the boundary is a curve, so this would be an integral over that curve. Okay, this term, but since the boundary is just 2 discrete points, that's why it came out as a just subtraction of 2 terms at the boundary. Okay, now let us discuss about this term. What all options do we have? Okay, once we have the weak form, suppose we don't have specified any boundary condition at this point in time, so what option do we have? Either v could be 0, v at L could be 0, u dash at 0 could be p, u dash at L could be q. Okay, what does these things mean? Note that v is nothing but any vector in the vector space V in which you are searching a solution or the part of the solution. Now, so these terms satisfies the Dirichlet boundary condition. For example, if Dirichlet boundary condition is specified at u is equal to 0, then this term v0 would be 0. If it is specified at L, then this term would be 0. If both, then both would be 0. If none of the Dirichlet boundary condition is satisfied, then these things need not be 0. Okay, and these conditions are for the Neumann boundary condition. If you satisfy Neumann at 0, it will be directly equal to p, and if you satisfy at L, it directly becomes equal to q. So this thing depends on the problem that you are tackling. Okay, so these are all things that you can have. This is how you handle this this part of the weak form. Okay, now note that this we just need to make sure that this basis function that we are choosing should be 0 at the point that the Dirichlet condition has been specified. We are not concerned about the Neumann. So do you think that we'll be able to satisfy the Neumann boundary condition? Actually, the answer is no. The direct answer is no, but if you go on increasing your dimension of your space, you would be able to reach to a point that in some sense you are getting closer to satisfying the Neumann boundary condition. But unlike the case where we constructed the superior boundary functions to satisfy these conditions here, because since we are not enforcing these Neumann boundary condition in our actual solution, in the trial solution, and we are not generating those superior boundary functions, those conditions may not be satisfied exactly. Okay, but but using some information of the Neumann boundary condition, this weak form helps us put in the value of this information in the Neumann boundary condition into your solution. So your approximation is, it does contain the information of your Neumann boundary condition, but it may not be exact. And if, as you go on increasing the dimension of your space, or for example in FEM, if you keep on discretizing your domain, you approach toward you approach towards satisfying this Neumann boundary condition exactly. Okay, don't worry if you don't know discretization and reducing the mesh size in FEM. You don't know that, but just if you know a bit of FEM at this point, you can relate these things. Yeah. So in short, these boundary conditions are not satisfied exactly if you are using weak form and using approximate function in the weak form. So out of these, you can have any two for a second order ODE, and it depends upon the problem which specific two you want to select. Okay. So now we are going to discuss different types of general boundary conditions in our domain. In this series, the domain would be spatial, a geometric domain in x, y, and z coordinate. Okay, first start with 1D domain. So in this domain, there we just have two boundary points. Okay, this one and this two, both extremes, and we call this gamma t and we call this gamma u. Why gamma t? It comes from structural mechanics that we are specifying traction, and u for displacement. So it basically means that you are specifying the Dirichlet boundary condition, and gamma t you are specifying the Neumann boundary condition. Okay, let's look into 2D domain. In 2D domain, this boundary is a curve. Okay, this pink part is where we have specified the Dirichlet boundary condition, and in this blue part, what we have specified is a traction boundary condition. You can extend it to the 3D also. In 3D, these boundaries would be surfaces. Okay. Now, yeah. So this is what it is. The pink one is where the Dirichlet boundary condition has been specified, and the blue one is where Neumann boundary condition has been specified. Now, some condition on these boundaries. Okay. So called the complementary nature. What does it mean? Let us see. There are two properties. Okay, the Neumann boundary condition and the Dirichlet boundary condition cannot be specified at same boundary point. Okay, you can understand this by using an example from structural mechanics, that you can't specify the force and displacement at the same node or at the same point in a domain. It doesn't make any sense. You are fixing at some point and also you are applying a force, so it doesn't make any sense. So these things you can't do. Okay, you are over specifying things, and one of them should be redundant. Okay, so this is the intersection of gamma t and gamma u should be 0. And what about the union? The union should be the complete boundary. That is, there shouldn't be any undefined part of the boundary. So we can't have any boundary part at which neither Neumann nor Dirichlet boundary condition is satisfied. Okay, so you need to, for completely formulating your problem, your complete definition of your problem, you need to define everything on your boundary. And by specifying everything on the boundary and using the differential equation or the partial differential equation, you calculate everything inside the domain. Okay, that is dependent on the physics of the problem. That is, this information is stored in your PDE. Okay, so these are the two conditions that we need to satisfy. Again, so a caution now for in the weak form. For example, in the weak form, this, if somehow you by mistake you neglect this boundary term, okay, what happens then? What you have assumed that V0 and VL is equal to 0. because you have not specified the value of u dash. By neglecting that, it means this thing only. So what you have done is you have specified v0 and vl is equal to 0. This means that you have assumed unintentionally homogeneous Dirichlet boundary condition to be applied at the boundaries. Okay, the for 1D case, it assumes that you have unintentionally applied the homogeneous Dirichlet boundary condition. So it's very important you keep track of this factor properly. Okay. Now, by doing this integration by part, what do we gain? Let's summarize those things. The first thing, it weakens the differentiability requirement. Okay, because we have transferred one derivative from our approximate or the solution, a state variable, to the vector in which we are, or the vector in the trial space. Okay, I'll just simply show it right now. So yeah, what we have done is we have converted this into u dash v dash. So now the differentiability requirement of a trial solution, when we put our trial solution in this expression, is now reduced. Okay, let's now move back to where we were. Okay, so we have weakened the differentiability requirement of the approximation of u, and so now the lower order polynomials can be used as basis function. Yeah, we'll see that later. And Neumann boundary conditions comes out naturally, and you need not construct your trial function in such a way that they satisfy the Neumann boundary condition. So it's now easier to handle. Neumann boundary conditions are now easier to handle, and these transformation result in symmetric matrices. That is symmetric A. The A matrix that we were solving is now symmetric for special type, not for all problems, but for special type of problems. They are called self-adjoint systems. Okay, we get linear equations, and they are very easy. The symmetric matrix are easier to solve. So that is also another advantage of converting your weighted residual statement to a weak form using integration by part. Okay, so let us now discuss weak form in detail. So we also call it the variational form or the V form. Okay, so the equation that you obtain after integration by part is called a weak form. That's what we have discussed. Okay, now the weighted residual form was this. We perform integration by part and we got this equation. This is nothing but the weak form of the governing equation. Throughout the series after this point, we'll be solving only this thing. Okay, up till this point we were solving this expression and we faced a lot of problem. Let us call this a weighted residual form, and now we'll be solving this weak form or V form. Okay, look at you can see that there is no approximation introduced up to this point, just the exact statement of your governing equation. Now let us try to abstractly represent the way we abstractly represent a differential equation. Let us try to abstractly represent a weak form. Okay, so we represent it in this form as AUV is equals to LV. A is nothing but a bilinear form, a bilinear operator which contains both your weight and the solution, and this part contains only the trial solutions. Okay, only the not trial solution, just the basis functions of or this is actually the any vector in your space V. So this is this term. This term will become clearer in the example that we are seeing right now. For example, this is our weighted residual statement. We converted it into a weak form by integration by part. Now you can write it in this form also, okay? Just rearranging things. So this term contains u dash and v dash, and this term contains only v. Okay, and this is not a function u, this is a ul, this is a scalar value here, correct? This is not a function right now. Okay, so these terms are now called as, this is AUV, this is called BL of V, a linear operator and a bilinear operator. Why are they bilinear and linear? because of some of the properties of these things. Okay, those properties are bilinearity and linearity. So linearity and bilinearity is satisfying this expression. Okay, if it distributes in both the arguments, say a u1 plus u2 now distributed, a u v1 plus v2 is also distributed. If you multiply by a scalar, it comes out. The linearity is simply this l v1 plus v2 is l v1 plus l v2, and if you multiply by alpha, it comes out. So this is just what bilinearity is, nothing but linearity over both the arguments. So one thing that we want to clear at this point is this form, this a u comma v is equals to lv for all v in v is only obtainable for specific class of problems or linear problems. Okay, such kind of linear operators. But if your differential equation or the partial differential equation is non-linear, then you won't be getting this kind of form. You'll be getting some f u of v is equal to 0, some random collection of u and v integrals and various other stuff. So you won't be getting a very good nice linear form or linear abstract form of your PD. So this abstract form that we are discussing here is applicable only to linear PDs. Okay, so in this series we'll be discussing only linear, so you need not worry about this. Just consider that the weak form can be represented in this abstract form. Okay, so that's it for this video, and we'll look few examples of solving the ODEs using the weak form in the next video, and implement the same thing in Matlab. Thank you.